Thank you. Thank you very much. Also, thank you for asking me to present. I have to say, I'm no longer working at an institution like JPL or LIST for that matter. You know, I've got a long history of jumping around the world. So you will get a much less technical presentation now, a bit more of an overview of historical things, and then I'll move on to the GFM, the Copernicus Global Flood Monitoring Service, which we have a bit of experience with, and there's some great stuff, some not so great stuff. So in order to have an objectivity, instead of me complaining about it, I use actually a very recent this year published scientific paper by someone who is actually doing the service. And so everything summarized and pains and limitations is actually scientifically published. I just want to highlight that because I have my own company, but I do this really from a science perspective. So I also want to make sure people understand that when I do complain, I complain about myself, probably as EOTEC DevNet, not as a business person. So I will get this to full screen if I can, and let me know if you see this. Okay.
Oh, it's okay.
Okay, great. So I was asked actually to talk a bit more about SAR workflow and lesson learned. So I will focus on lesson learned. So I give an introduction. I go a bit through the breakthrough milestones in history that I think happened from a flood mapping perspective and satellites. I published actually a while ago these 6 breakthroughs, and 2 of them are actually very SAR driven. It got accepted, but of course, this is my opinion, but it could be others, could be added or not. And then I focus really on the Copernicus Global Flood Monitoring Service, because I think it's a great initiative, but it has its challenges. And there is just been a tender has just been closed where the commission asks for a revamp of the service with probably new algorithms, new things. So hopefully some of the challenges will be addressed. But the great thing about it, it's under the Copernicus program, so it is an operational service, and it will probably not so easily disappear, but it all depends on the new scientific things that can be done for improving it. By the way, this is an ERS2 image. So I did most of my PhD on European remote sensing satellite, the second one. And over the years, starting mostly at JPL, actually, I got a lot exposed to what Erica was talking in the presentation about Opera, like end user, bringing end user to the table. And I worked a lot with the UN World Food Program on flood mapping when I was still at JPL, and it just opened my eyes about what things work and what things don't. If you needed the satellite to be there over a flood anywhere in the world, it's not there. And typically it's also a clouded optical image. And when you hope for SAR, you actually need really what I just said, you need to hope for it because you have no idea whether it would be there or not. So now the whole thing has changed with, of course, Sentinel SAR 1D launching. I'll mention this a bit further on, and NISAR and everything else. So we're a bit different now. I also then looked at these breakthroughs, but more recently I tried to also publish more like magazine style things where I bring this to everybody, just the big messages of space and what's possible to do for flood disasters. So this is from an image that I created, what I think are the really breakthroughs of flood mapping from space. So of course, and maybe Kathleen, you can answer this once, or I don't know if anybody wants to answer this. My biggest question was, why did JPL stop SAR after late 80s and didn't come back until very recently? But I think I know the answer, but maybe, so that would be my question to you later. Anyway, so in 1970s, early on, Landsat was launched and showed the world that indeed you could take a lot of environmental images from Earth. And lucky enough, it took an image of a flood in I think Pakistan, Mississippi, and you could see, this is the Mississippi. It gave you the impression that you could now see all the floods from space, and you wouldn't need to worry about disasters anymore, and prevention and all that stuff could be done. Of course, that was a bit of a promise, but in the early 80s, I think this was on the shuttle, JPL launched the CRB mission, so a SAR instrument on the shuttle, and it recorded also, quite by chance, I would say, a huge flood in Bangladesh, and through very thick cloud cover. So it was a tropical cyclone, a huge one, and they saw it like this, so as if there were no clouds, and this is the kind of most relevant feature of SAR. It penetrates all weather, rain, and so day and night as well, it doesn't really matter. So that was great. We could see that. And then in 2000, I think the international charter got launched by European, ESA and the French Space Agency. This was a great initiative, I think, probably one of the best initiatives for disasters and satellites. It includes all major agencies and also now, I think, commercial satellite providers giving data for free when there's a disaster. And then these data can be used for a couple of months or so to map, or more if it's not a commercial. And these maps are done also openly available. And if you are subscribed to the disaster charter, you will see that floods is by far the most unfortunate leading disaster that gets activated and triggered. Global potential was again shown by NASA, Aqua and Terra missions having MODIS, and we were now seeing that you could, if you're fortunate enough, but clouds move also, so twice a day you could actually map floods from space anywhere on the Earth. And then 2014, the Copernicus program, I think, was the operational program, truly operational, because it's actually embedded in the European Commission and not at ESA. So it's truly operational. It has a mandate to stay like that. And it's the Sentinel missions that feed that operational program. And the first satellite they launched was the Sentinel-1A. And now we are at number D, but do remember we lost one of them. I say we, I consider myself a European. So I guess it's also not ESA that lost it. I think these things happen. Space is risky, but it's great that it's an operational series. So you see it got then C and D. So it doesn't, it matters. It's a lot of resources lost, but the operationality is preserved. And 2019, I think I wanted to highlight this because I was involved with the students and postdoc on this FDL challenge. They actually put a machine learning algorithm to map floods. They showed that it could be put on board a satellite and process things in space itself, something like floods. So this was tested also in an orbit flight with the orbit, but again, I think these are the milestones, and I haven't seen anything that I would consider a milestone because it may have been shown in these 6, but I may be wrong. So somebody would need to redraw this in more recent years. Then here, the breakthrough bit, I'm going to focus on one here only. It's the number 5 is the Copernicus program with Sentinel-1 because it leads to the GFM, so to the Global Monitoring Service, because it is actually open access operational satellite data. So something you would expect from NOAA or EUMETSAT in the metrology now is available for land surface mapping on the low Earth orbit. And this with SAR. So why do I say this is like a milestone? While the barrier lifted was before the Sentinel program, I think it was all just opportunistic with SAR. So when you had a SAR image, you were kind of lucky. Now you can actually get with the 4 satellites now up there, or 3 satellites, sorry, you can get really below a few days. So you get really high resolution and high temporal coverage with SAR. And if you then add missions like NISA, yes, they are scientific, explorative, but at their lifetime, they will add enormous data volumes to operational SAR. And do remember SAR, the Sentinel-1 is a C-band, so it's not great for what was shown on the Amazon. You wouldn't get much of a response from the flooded below the tree cover, because actually most trees on the Amazon are very tall, and C-band, if I remember a bit correctly, is not reaching more than 50% down, so it will never hit and come back again through the canopy, the flat surfaces below. So you need L-band or longer to do that. So I do think this L-band global coverage with NISA is absolutely amazing. Even more so because the Germans cancelled a couple of years ago their L-band mission that was supposed to be launched from DLR. Anyway, so really glad to see NISA. C and X-band has a history of SAR mapping. X-band started more or less with, well, it started actually with, as ATM also had an X-band, but the TerraSAR is a very high resolution dual mission from Germany that we all know, that has been launched in 2007 and is acquiring great images of floods as well. ERS-1 and ERS-2, I would call them the European legacy missions. They're great. They provided really useful disaster imagery. And VSAT was the beast of ESA, so multi-sensor on one platform, and it had a SAR. It was called advanced SAR, but it's not really advanced now if you compare it, but it was able to change with image modes as well, like 175 meter, for example. And you could get really large image swath over regions. So it was fantastic to look at large floods like Australia or the US as well. Here's just the comparison. You know, if you say, well, SAR is great. If it's not cloudy, optical, I would dare to say it's always easier to interpret. This is just a comparison between a huge Queensland flood, absolutely cloud-free, with Sentinel-2, absolutely an amazing image, compared to what you still have to look at it from a scientific and signal complexity, a Sentinel-1 in the Balkans, in Europe in 2014. So there's a huge difference between these two with an ease of interpretation. And here I think I really need to show this, because the commercial sector has moved into SAR with ISI constellation, very high resolution. I showed this company only because they are also doing flat mapping, although I don't know how much you have to pay to get a flat map from them, but it's proprietary, it's payable service, but it's great. And sometimes they do fly over a disaster and then post their flat map somewhere as a photo or JPEG, and you can actually see it's also using kind of a merge between some hydrological modeling and SAR signal, but it starts off from the SAR map, so it's really nice. And I think we are now in a world where probably the best option is to look at partnerships between public-private, because if you bring in this type of constellations with the other SAR that are publicly available, you can really get an amazing coverage. But sometimes companies don't, or often they don't free up their data like public missions do. And of course, sorry, I should have mentioned, when I mentioned TerraSAR, I forgot Cosmo SkyMet. Sorry to the Italians. It's actually an amazing mission because it has more satellites up there than TerraSAR, and it's X-band as well. But there is the Cosmo SkyMet mission, and it is available for science as well. It's just not easily available. You have to go through procedure, but similar to TerraSAR. So great missions. I'm going to spend the next few minutes to talk about the power of SAR operationality. Is it really there with the GFM? So there's the paper I was talking about, released this year, actually at the launch of the Sentinel SAR 1D, coincidentally, this paper. So I think it's very good for Wagner's group in Austria to have that coincidental day. This is just an overview, and it's part of the what I call the fifth milestone. It's really to get the Copernicus program launched and to look at what can you really do with the Sentinel-1 constellation. And the idea was to create automated global flat maps. And of course, it then leverages only at the moment the Sentinel-1 SAR. It doesn't include any other SAR, although I guess it could, but it's very European focused. So that's the main reason. And it looks for this operationality. So I think Sentinel-1 constellation is the only one that meets those criteria. And of course, as I said before, it looks through clouds and operates regardless of light conditions, so night as well. But the real main advantage is it actually starts using many hundreds of terabytes of data in a cube. I think that's the real challenge. It really is massive big data, and it can actually do it. So it's the full automation. It's unlike previous. You have on-demand services. You say, okay, I'm lucky. I get a SAR image. Now I need to process it manually or with a machine, but I still need to do it on demand and not fully automated. So this also changed a lot. And I think they only used VV polarization in the Sentinel-1, but it's really fully automated. So I go a bit of what I call the good, the bad, and the ugly. The good is, of course, as I mentioned already, you have the global data cube. It's really a cube of all SAR. It's fantastic. And it does that with new images and historical data as well. So it's back processing, but it's also now taking any new image coming in, any new image, and it's constantly processing those. And if it's not a flood, it throws it out. Because if it's a flood, it applies a number of algorithms, and that's why the ensemble approach is very nice as well. It combines actually 3 independently developed flood mapping algorithms. One is from DLR, one is from Luxembourg Institute of Science and Technology, LIST, and the third one is from TU Vienna, whose group also wrote the paper I got most of this messages from. Output layers, there are many output layers. Actually, for end users, maybe there are too many. But for science, it's great. You have binary flood maps, you have a flood likelihood layer because you have multiple algorithms. You have permanent water, you have seasonal water, but you unfortunately have an exclusion mask. And I'm going to spend a bit of time on that. The exclusion mask is actually, scientifically speaking, it's a great layer. From a practical standpoint, if you're an emergency manager, or you are from the humanitarian services and you want to do assistance, it's really a bad layer, because it tells you that in most places on the earth, SAR C-band is not great. And this is true scientifically, but it's just disappointing for most end users. And I know that because I had a lot of requests from the UN saying, why is there no Sentinel-1 GFM in places like, I don't know, in vegetated places, in urban areas? Where is there no why do you not process these? And it's not that we don't process these, it's that these are impossible to process because SAR C-band doesn't see those floods for obvious reasons. So approximately 70%, according to Wagner's paper, are covered by exclusion mask. But do remember, these are the global land areas, so also deserts are part of exclusion mask, but also a lot of floodplains. So this is not great. And it includes typically unreliable data due to dense vegetation, forests, urban structures, or topographic distortions. Now think about how many things of these 3 alone can sit on or happen on natural floodplains. So complex scattering, then we saw a lot about that in the previous presentation. It's really difficult to get a SAR signal. So this is kind of part of the exclusion layer, but it's really difficult and it's really not very good. And it also includes things like water lookalike surfaces, airport runways, sand, all these things, they look in sea frequency similar to open water. So it's not fantastic. But the new tender that came out for a new algorithms was actually calling to address or try to address these challenges in one way or another, with the same frequency, with the same constellation. So not sure how much improvement we would get on those with the second, let's say GFM 2.0. I don't know. I'm nearly done, so sorry, I'm taking a bit of time. This is part of the paper as well. This is just a nice illustration. It shows you how the decision-making tree is done of the three algorithms, and it indeed comes down. It's just giving you a higher confidence that you actually see a flooded surface if you have more than one algorithm agreeing on that flood. And that's the purpose. And the other graph is just a nice illustration. It shows you how much time each processing step takes and how fast they need to be to stay operationally meaningful. So in terms of performance and accuracy of the GFM, I would say they're typically delivered in 5 hours of image acquisition, which is absolutely fantastic. Just think about satellite acquiring. You need to bring it down, the image. You need to process it into SAR, into an image. You need to process the SAR into an image. You then need to release it to a cloud and then a cube. And then you need to run these three algorithms. So all of that is 5 hours. I think it's quite fast. Regional performances. I think initial results reading that paper show high accuracy of large-scale floods in temperate and tropical zones, while accuracy is lower for smaller floods and arid environments, which makes absolutely logical sense to me. So the cube and GFM is still not mind-blowing, but it is getting a step closer to what we can do in operational flood mapping. And we know that we have NOAA VS doing operational flood mapping with optical. So if you take the GFM SAR and you look and you combine it somehow with the operational flood mapping from NOAA VS, you really get a lot of floods mapped. Future direction, and this is a nice picture of the Sentinel-1D launch in November 2025. The future directions, I would say, is to enhance data. So the plans include to incorporate the other polarization available. So they were just processing VV for now, but it should look at VH as well, because it would help apparently to look at floods in vegetated areas, although I'm not very sure, because it depends on maybe short vegetation, yes. Trees, like in the Amazon, definitely not. Upcoming missions, the service aims to integrate data from future missions. I don't know about that. I mean, the mission needs to be there first before. I think that's why the word aim was in the paper. Algorithm improvement, definitely there's continued development focusing on refining algorithms. That's very true. So we do get improvements, and we should not get degradation in services, but more improving. So, and to reduce this under detection of SAR that we typically see. Anyway, that's me. I stop here. Maybe we have 5 minutes for questions, but yeah, here's my email. Feel free to write to me if you have questions. I've also got a number of students here that could answer your questions maybe better than I can. So thank you.
Yeah, thank you very much, Guy.
Thank you.
And yeah, very nice presentation. You mentioned that you are not in a company, but you still have a very scientific view of the problem.
I
But
hope so, yes. I'm just getting, I think, old for this era because we're moving fast. We're moving way too fast for me, because also in the new tender, there was a lot of push towards putting AI and machine learning into the new algorithms. And as far as I can remember, I think the last version, so the three algorithms I talked about, I didn't actually mention it, but none of them is machine learning driven. Maybe DLR a bit, I don't know, I should check, but not much ML. And I have a feeling that the new wave of algorithms will include a lot of that, indeed. Whether it's automated clustering or something like that, but I think there will be some in there, indeed. Yeah, no, thank you. Thank you for...
No, but then the other point is that always we have this false expectation that currently with SAR data, we solve the issue of getting flood mapping quite easily.
No,
But
we don't.
it's not. No, yeah. I'm working also together with Wolfgang and others. And yes,
Actually,
always.
Actually, if I can add this, the dream would be you take Cosmos Skymet, the constellation, you take the RadarSat-2 constellation, because they are very similar controlled, it's dual missions both. But if you look at what happens when Italy experiences a landslide or a flood, if Cosmos Skymet becomes available, the game of having a good flat map changes immediately, because you get a really good flat map. And you know better than me, for some regions that were massively flooded, it was a disaster for Italy. If you then have access to Cosmos Skymet, you get a lot of things also in urban or very close to urban areas. Of course, you then need the experts to process that, but these missions also come with these kind of scientific people that can then actually handle those data very quickly. And I think my dream, I imagine in my head, would be that we would have maybe machine learning aided, but we would have things that you just go on a platform, you click on an area, and half an hour later comes your flat map at the resolution you wish, and you don't even know which satellite was used to do that. That would be the ideal solution. But indeed, we are far away from SAR Sentinel-1 being there when you need it. And the exclusion mask is a huge problem for the practical people that need a map to take some action to rescue people. Yes.
Yeah. Then Martina posted in the chat about
Yeah,
somebody.
Yeah, so
Okay.
we had a presentation from a colleague from Miki Maganini from NASA. He was presenting what he's doing within the NASA Earth Rise initiative, and that right now he's working on intercomparison of different flat products. So here I shared a link to the GitHub. So if you are interested, feel free, and he will be also happy to share the link to the paper when it will be published. So I think it could be also of interest for you.
Okay, so that is existing codes, existing flat mapping algorithms that are compared to each other, right? If I got this right.
Yeah, the flat monitoring products.
Yes. Great. Yeah, thank you for this. This is very nice. Thank you.
Yeah, even myself, I was not aware.
No, I was not aware either. So that's why I reacted like this. Okay, this is very good. Yeah,
That's
thank
when EOTEC DevNet is here.
you. Yes, exactly. Good point. Yes.